Welcome everyone. In this video I'm going to start a video series which will be all about the CH32 microcontrollers. More specifically, I will use the CH32V003 microcontroller. So one of the main reasons why I picked this chip is because it's very cheap. I can buy a lot of 50 pieces for $15, so that's very nice. But also there is another reason, is that there was a really big hype about this microcontroller about 1.5–2 years ago. I don't know the exact date when it started, but then this kind of decayed. So even today, if I search for this specific microcontroller on YouTube, there are only a few good demos and projects, but there are no really good tutorials on it. And even big YouTubers seem to neglect these microcontrollers, and when they use it, they just only use it so they can push their affiliate link for this microcontroller and earn some money, but they don't really have any added value for this chip. And yes, of course, I will also share my affiliate links on my website, but in exchange for that you will see a very detailed video and a very detailed tutorial article on my website, so I think it's fair enough. And when it comes to this chip, and more specifically the F4P6 chip of this microcontroller family, then the closest popular chip that we can find on the market is the chip on the Arduino Nano. This has a slightly higher clock, or slightly, I mean 3 times higher clock, but the flash memory is just half of the Arduino Nano's flash memory. However, the rest of the peripherals and the GPIO pins and ADC, they are more or less the same as on the Arduino, so that's really nice. But of course, as I earlier mentioned, this chip is not that popular because there is no good software support for this yet. However, Arduino, we know that it has been building its community for like nearly 20 years. So of course there are a lot of libraries and stuff like that, and a lot of documentation and projects. But this chip is much younger, so yeah, we cannot expect a good amount of resources all of a sudden. So when we look at the website, which is linked in the description, we can see everything about the chip. But if we scroll down on the product page, then we can see that there are 2 data sheets. And if I open them, then these are those data sheets, and I really recommend you to get them and study them, because they will help you in coding. So this is the data sheet, and then this is the reference manual. So both of them are needed because they will help you to understand how the chip works. And coming back to the page, there is this evaluation board manual and reference routines. And this is basically a bunch of libraries filled with codes specific for different peripherals. So basically these are tutorials as well, but they are not really documented. So it's not really explained what is happening in the code. I will base my codes partially on these codes, which can be found in this zip file, but I will further expand them and I will explain them more carefully than it is done in this zip file. And finally, we need the development environment, which is this Mount River Studio. So just install it, and then it should work out of the box. So here you can see a bunch of boards and 2 programmers. So the boards are this, and these 2, and they have exactly the same chip. These 2 green guys are directly from the manufacturer of the chip. So this is the microcontroller evaluation board, and this is the corresponding programmer. And then this is basically the mirror image of that, but it's not from the manufacturer of the chip. So this is just some random AliExpress hidden gem. So this chip right here is a dev board also, but it's on a much smaller PCB. And then this is a programmer, but these 2 guys are equivalent, and these 2 guys are equivalent as well. And then these are also just a different type of development boards with the same chip but different packaging, as you can probably not see because it's not focusing, but yeah, you can believe me that they contain the same chip all over the place, but they just have different packaging. So what I'm going to do in this tutorial series is that I'm not going to use these because it would be just too easy, and I'm not going to use these, but I will build the tutorials with these two hardware. So once again, this is the programmer and this is the chip on the development board. And maybe what is worth mentioning about this tiny programmer is that this is not only just a programmer. So what we have is that here's a USB connection, yes, but on these pins what we have is that we have the single wire debugging interface, plus we have a serial interface. So actually the way we can communicate with this development board via the serial terminal on the computer is that we connect the RX and TX pins on the development board to the RX and TX pins on the programmer, and then the programmer will forward the message to the PC or the other way around. And today's tutorial series will be about GPIOs. So I have already prepared a demonstration board for this. So I will keep this breadboard on the picture, and you can just see that here is the programmer, and that will be just outside the picture because I will connect it to the computer via a USB cable. But basically this will be the hardware setup, and I think the picture is clean enough or clear enough that you can see it properly and you can figure out the connections of everything. But of course, again, go to my website and you will see more details and more information. So now I opened the development environment and now it's empty. So I'm going to create a new project so I can show you how we can do that. So we just go to File, New, and then Mound River Project. And then we have to select the corresponding microcontroller, so V003. And then as I said, we use the F4P6. So that's what we select here. And then we can name it like this, and then just finish. So now I created the tutorial. So now I opened the tutorial in the Project Explorer. And as you can see, I also opened the user folder, because in the user folder we have the main.c, which is the source code file of the project. So that's what we need to use. So this is the default main.c file. I just increased the font size a little bit and closed some unnecessary windows so we can see the code a bit better, hopefully. So what we can see here is that there is a small explanation about the code here, and the authors of the code already said here that there is a USART1 communication already implemented. And they also write the hardware connections here. So the PD5 pin is the RX and the PD6 pin is the TX of the microcontroller. If we open the datasheet, then we can also confirm this. So we have PD5, and that is indeed the TX, and we have PD6, which is indeed the RX pin. So this is just a simple chip diagram from the datasheet, and then we just confirm that okay, PD5 and PD6 is used for the USART communication. So now I'm going to clean up this code a little bit so we can do our own stuff in it. So we don't need this value, and I'm not going to change this config. Actually, I'm going to expand this, but first let me clean up this part. So I'm just using this function. So it's just the initialization of the USART, and then I don't need to print these on the serial port. And then here we are not going to send anything to the serial port just yet. So I clean this. And now if you are already familiar with Arduino, then what I can tell you here is that this part of the code is the same as the setup part in the Arduino code. So this just runs once when you start the microcontroller. And then this, you can see that this is an infinite loop, and this is actually the loop which is in the Arduino code. And this will run over and over. So after these things ran, let's just print something on the serial terminal just to make sure that the chip is running. So actually for that we can use the printf function. And then we just write whatever we want to print in it. And maybe it's good to print a delay before, because sometimes the code can run too fast, so we cannot catch this message in the beginning. So that's that. So now to get the code on the microcontroller, we have to compile it first. So I press F7. And now I have to upload it, and then I press F8. So this is done. So let's open my favorite terminal software, CoolTerm. So here is CoolTerm, but nothing appeared here because the microcontroller was already running, so the serial port was a bit too late. So let's trigger a new printing. And there you go. We wrote our first, let's say, hello world program for this microcontroller. And we can print messages on the serial port. And it is so easy. It's printf, and you write the string in it, and then it works. But of course, this tutorial is about GPIOs. That's why I have a bunch of LEDs and a bunch of buttons on my breadboard. So let's develop some code related to that one. So let's return to the breadboard a little bit. And as you can see, we have the 4 LEDs here, and they are wired up to 4 different GPIO ports. And those GPIO ports are to be found on port D, which are pin 0, 2, and 3, and I selected pin number 1 on port C. So what we need to do now is that we need to tell the code that these are actually outputs, so let's do that. So we have this already existing code to define some pins for the USART, so let's recycle a little part of it. And then we do like this. We created a function. And then I need the structure for the GPIOs. And I need the clock for the GPIO D plus the GPIO C. So I'm going to replace this and do like this. So now the clocks are also provided for these 2 ports. And now we need to fill in this structure with the GPIO speed, the GPIO mode, and then the GPIO pin. So again, I'm stealing from here a bit because I need these 4 lines. And I go back, do like this. And we know that we have GPIO pin 0, and then 2 more pins, which is pin number 2 and pin number 3. And if we want to define all the 3 pins at once, we have to combine them with the logical OR operation, something like this. Because at the end, what happens is that these are actually just numbers. So you can see that this is 008, 004, 001. And then these numbers, or this number, is passed to the corresponding register. And the register, based on the value, will know which pins should be turned on and off, and so on and so on. So actually we can just combine these 3 numbers into one number, and their result will actually tell the register that this is actually several pins. And then the speed can be 30 or 50 megahertz or other speeds, which are declared in another header file, but we just keep it at 30. And you can see that now the GPIO mode is set to AFPP. And what means here is that the AF is the alternate function, because if we look at the datasheet, we can see that other than the GPIO pin association, we have, for example, an analog association here. So we can use the PD4 as the 7th channel of the analog input, or this UCK is also there, or this timer 2 related channel, or the timer 1 related channel, or this OPO, and so on and so on. And all these pins have several different functions. So that pin definition meant that we are using one of these alternate functions. But we don't need that. What we need is that we need to define this as an output in a PP mode, which is push-pull. So we can manually set it either to low or high. And then what happens is that when we created these 3 lines, then actually this mode, speed, and pin values are passed to this structure, and then this structure is, let's say, filled in, and then its memory address is passed to this GPIO init function, and then it is applied on the GPIO-D port. And we have a GPIO-C because we have the PC1 pin as well. So let me do that. That is just one single pin and on the C port. So that's nice. I'm not entirely sure why my code is falling apart, but now it's nicely formatted. And then I copy this function name and place it here. So now we initialize the LEDs. But now we need to toggle these pins that we defined here as output. So we need another function. Let's just call it like this. On a deeper level, what happens here is that we have the register for the corresponding pins, and the registers hold some values or bits, and those bits can be set or reset, or with other words, set means high and reset means low. So we have to write these bits. So we need to call this function which writes the bits. And then you can see that the argument here will be 3 different things. The GPIO port, the GPIO pin, and then the bit value. So basically we can say that on port D at pin 1 we have to set the value, or we want to set the value to reset. So then that specific pin will be set to reset or low. But we have GPIO-D, that's fine. And then if we remember, we have a GPIO pin 0. And now I want to do a trick here. First I read the status of the pin, the current status. So then we have to read the output bit, which is done somehow like this. Read output data bit. And then I read the same port, and then I read the same pin. And then what I do is that if this value is bit set, then I set it to bit reset. Otherwise it will be bit set, so if it reads reset. So what this does is that it like kind of automatically toggles the pin. So first it reads the pin's current status and it sets the pin to the opposite status. And then we do some delay, which is, let's say, 50 milliseconds. Nice. And then I copy paste this 3 times, because we have pin 2, we have pin 3 on port D, and on port C we have pin 1. And now let's run this multiple times. So let's do like this. Let's make it 20 times. I++. So this and this. And now let's put this in the setup. So after we initialized the LED GPIO pins, we blink the LEDs 20 times or toggle them. So let's see if this works. I switch to the other camera. And we are still here. And I compile and I upload. and it works. Obviously, they did not show up in the same order as you would expect, let's say from left to right or right to left. I don't care. That is just about the order of pins in the code or the order of wires here, but we just wanted to toggle the pins. So this part of the lecture is done. So now we know how to write on the GPIO pin, how to set it to high or low, so we can toggle it. But now we want to be able to read it. So what we should do is that we should pull a button and run this function when the button is pressed. So how we do that is the following. I created a function, and then what we do is we create an if-else statement first. Something like this. So in the if, we need to read the input data bit. So we basically read or digital read the GPIO port. And then let's say we do it on the GPIO C and on pin 0, because that's how I wired my button. And then we see if its status is bit reset. And why I do this is because how I wired the buttons is that they are pulled up with a pull-up resistor to high. So when you press the button shorts the pin to ground, and then also the GPIO pin goes to ground. So we look for that status, and actually that's what we do here. So I just copy this guy, and it's done. And I do a cheap man's debouncing here, like this, because the button is not perfect, so it can bounce. So the debouncing is done, but the code doesn't know that this is an input. So we go up here, and we just expand this function. So what I simply do here is I copy this, I press this to PC0, and then I have to change this to input and floating. And it's floating because we use an external pull-up resistor. So this can be this. This can be the function. So this is done. Then let's go back to this function and let's run this in the main loop, because we need to pull the button. Now I change cameras and I upload the code. And you will see this blinking, because this is just the startup code. And now I press the button. And you can see that it does the blinking if I press the button, because the button was pulled and the button detected that it was pressed, so it was pulled down to ground, or more specifically the PC1 pin here got pulled down to ground, and then that triggered the blinky function. Then, since we have some USART code already in our source code, right here, we can use the USART as well. So let's combine them with buttons. So what I'm going to do is I'm going to use two buttons, and one will increase the value of a variable and one will decrease the value of a variable. And then the value will be sent to the serial port. So actually we can cheat. I can do this. And then I can explain what is happening. So I will pick two other pins which are available. One will be the PC2 and the other will be the PC3. And then this function must go, but let's say this should be button value ++, and then we use the printf function and say that this will be the text, and then we print the decimal value, and then a new line, and then we put the button value there. And then in the other button case, we decrease it. But now we have to do a few more things. First of all, we have to declare the button value as a global variable. So it's just a unsigned integer, or actually it can be integer, because let's print negative values. So like this, and this was called button value, and let's make it start from 0. So that's nice. And we have C2 and C3, which has to be inputs. So they have to be defined as inputs, which we can do actually right here. So actually now I'm going to cheat a little bit and copy this and add this and add this. So now GPIO pin 0, 2, 3 on the C port are defined as floating inputs, but they are pulled up by the pull-up resistors connected to the buttons. And then this is fine, but we need to run this function in the main loop, which is located here. So I compile it just to see if it works. And then let's see it through the terminal. So I'm now compiling this thing here. And then I press a button. And you can see button value 1 was printed, 2. And every time I press a button, this goes up. And then I press the other button, then it goes down. Maybe I do like this, just so you know and see what I'm doing. So I'm pressing this button, and then value goes up. And then I press the other button, this one here, and the value goes down. And of course, if I keep it pressed, then it continuously reads the reset value. But of course, it's not going too fast, because if you remember, in the polling function up here, like right here, we have 100 milliseconds of delay. So therefore, whenever I print something here, there is always at least 100 milliseconds delay. And of course, this should also work. So basically, this was the first parts tutorial. What I wanted to show you here is that we can read the GPIO pins and write them. So for example, we can detect a button switch, and we can switch an LED and whatever you connect to it, as long as you respect the amount of load that you can put on the GPIO pin. So you cannot put something on it which requires several hundred milliamps, for example. But an LED is fine with a corresponding current limiter resistor. And then a button also works, and there are other things that you can use to detect changes on the GPIO port using the polling technique. So this lesson will be the fundamentals for the rest of the series. And in the next lecture, I'm going to talk about the USART basics a little bit. And before you would leave, please consider subscribing my channel and also becoming the member of the channel, because that can help me a lot. And once again, don't forget to check out my website, because I wrote an article. Link is in the description. Every useful resources are summarized there, so check it. And visit the parts and tools section on my website, because that's where I store all the good parts and everything. So I took pictures of all the components that I'm using here, and then I uploaded it there. So you can use my affiliate links and indirectly support me with that as well. It doesn't cost you anything, but it can help me. So why not? So I hope this video was useful to you. I hope you learned something, and see you in the next video.